train with the dynamic range of FP16, which is about a 10 order of magnitude dynamic range. As long as we're willing to scale it per layer, we build automated software to do that scaling. In fact, the really critical scaling is that the dynamic range you have during the forward propagation, where you take, say, an image and run it through the layers of the convolutional network, is very different from the dynamic range you have during back propagation, where you typically have very small gradients you're propagating back through the layers. But if you scale those differently, the dynamic range you have to worry about at any given time is small enough to be captured in that 10 orders of magnitude. And then for inference, what we have found is that int8 is sufficient for most inference applications. And it's really critical to reduce the precision you need for these operations for two reasons. The first is that when you look at the multiply accumulates, the cost of doing a multiply, these are our numbers from my colleague Mark Horowitz at Stanford from a 45 nanometer process. The cost of doing multiply is quadratic with the number of bits. So if I go from an 8-bit multiply, which is this line here, to a 32-bit multiply, it's not 4 times more expensive, it's 16 times more expensive. Because I'm producing an array of partial products where the number of partial products is a square of the number of bits in each operand. The other reason why it's really critical is because if you have large numbers, you have to store them and move them around. And storing them and moving them around is really expensive compared to actually doing the arithmetic. Well, you may think that a multiply is expensive. I'm doing 8-bit multiplies. The cost of reading SRAM is an order of magnitude more expensive than doing that multiply. Even a small SRAM, an 8K SRAM, is right next to there. In fact, a rule of thumb I have is that every time you move up a level in the memory system, the cost of the access goes up by an order of magnitude. So reading that 8K SRAM sitting right next to your multiplier is 5 picojoules per word. Getting it globally on chip is 50 picojoules per word. And by the way, that's the same 5 picojoules to reference the SRAM. You build big SRAM arrays out of many little SRAM arrays. So you're actually referencing an 8K SRAM here at 5 picojoules. You're spending the other 45 picojoules moving down. That's basically driving wires from where the SRAM array is to where you're consuming the result. And heaven forbid you have to go off chip, even with an LPDDR DRAM, it's used for mobile products. Well, the lowest energy per bit DRAM you can get is still another order of magnitude more expensive to go off chip. So you have to avoid going off chip at all costs. Now, one way of making things even smaller than the 8-bit inference is to basically use deep learning to do basically non-uniform quantization. Suppose I decide I want to use 4 bits to represent the weights of a neural network. After pruning, which I'll talk about in a little while, the distribution of weights is shown here in blue. This is the probability distribution function, probability density function of these weights. And if I use uniform quantization, say integer representation, and I have 4 bits, I'll get 16 evenly spaced symbols, which are shown by the green X's here. But you can see that that's highly inefficient. I have a lot of symbols out here where nothing interesting is happening. When all the interesting stuff is happening, I'm sampling it very coarsely. So a much more efficient way of doing business is to basically do what's done by the red dots here, is to use a code book to sample where the interesting things are happening. So I sample very densely where the lobes of this distribution are. And I put only a few samples out in the outer reaches where it's not very important. What's really interesting is that you can use the same algorithms used to train our networks to train this code book. Anything you can differentiate, you can train with stochastic gradient descent. We can differentiate into this code book, take the partial derivative of the loss function with respect to the code words, and then use that to train the code words to find the optimal set of code words for a given function. This is work that was done by my former PhD student, Song Han and I, published at ICLR a couple of years ago, and Song is now on the faculty at MIT. And what he showed is that if you take this technique for fully connected layers, you can get by with 4 bits of resolution and have absolutely no loss of accuracy. And you don't get catastrophic loss of accuracy until you drop below 2 bits of accuracy. For convolutional layers, those numbers are 6 and 4. There's no loss of accuracy to 6 bits, where typically you would have needed 8, and you don't get catastrophic loss until you get down to 4 bits. So that's one way of reducing things, is to come up with very dense encodings. First of all, to use low precision numbers, and then where appropriate, to actually further encode by using non-uniform quantization. The other thing that we realized is also work that I did with Song that was published in NIPS in 2015, is that you don't need most of the connections. If you look at the brain's connectivity, it is very sparse. In fact, it starts out denser and gets sparser. We have the most neurons that we ever have when we're about 1 year old. And then our brains prune themselves and reduce the neurons and keep the useful ones and get rid of the non-useful ones. We can do the same thing with the connections here. In fact, what we do is we take a neural network and we train it dense, and then we basically lop out the lowest weight neurons. When we first did this, we had horrible accuracy. And then we realized that the missing ingredient was to retrain holding that sparsity constraint. And when we did that, what we found was the following. So we started out with a certain level of accuracy. So this is relative accuracy to the original network. And this, I believe, was results in VGGNet. And when we pruned it without retraining, we got the purple line here, which basically said if you took more than half the weights out, you started to lose accuracy. You'd have really awful accuracy as you got sparser. But if you retrained, which is the green line here, you actually got better accuracy for a while, and you didn't lose accuracy until you got out nearly 90%. And then anything worth doing once is worth repeating. So if you do that iteratively, you get the red line, and you can basically take 90% of the weights out. You throw 9/10 of the weights out and lose no accuracy. Now it turns out that especially if you use what's called a ReLU or a rectified linear unit nonlinearity in your network, you actually have also many zeros in the activations because all the negative numbers turn into zeros. So we found only about 30% of the activations were non-zero. So of all the multiplies you're doing for the neural network for a fully connected layer, only 3% of them have to be done. The other ones all have a zero in either the weight or the activation. And that's a huge advantage. So a lot of these things are grist for building accelerators. One of the first accelerators I built with my students at Stanford was called the Efficient Inference Engine. And what it was doing was showing that you could efficiently exploit sparsity at this level of 10 to 30% dense. If you talk to a numerical analyst, what they'll explain to you is that it's not worth using the sparse matrix package until your sparsity gets down to well under 1, your density is well under 1%. Because the overhead of walking the pointers and doing all the irregular access swamps that. But if you can build special purpose hardware, I can walk the pointers for free. Building some addressing to walk the pointer structure is very inexpensive to do. We can also compress the pointer structure, so having to keep 32 or 64 bits per pointer as in a conventional sparse matrix package. We can run length and code them at 4 bits per pointer. So the overhead of storing those pointers becomes negligible. We expand them through this accumulation process. Because we're doing train quantization, we basically have a code book that would be very expensive to do in software. It's absolutely dirt cheap to do in hardware. And we can basically get all of the advantage of sparsity and compression with essentially no overhead by using special purpose hardware to take the hard parts out of that. To show you that it's basically all about the memory, the green area here is storing payload data. That's actually storing the non-zero elements of the sparse matrix. The sparse matrix pointer structures are shown here on either side, and the logic is this little stuff in the middle. The logic almost doesn't matter, either in terms of area or power. It's all dominated by memory. We also went on, this is with part of my research group at NVIDIA, to look at how to do sparse convolutions most efficiently. And so it turns out here I have a sparse activation layer shown here in green. I want to convolve it with a sparse kernel of weights in a 3x3 convolution. And that will actually fill in the output activations until I apply the ReLU function after summing everything up. And the way we chose to do this actually is to observe that every one of these weights has to be multiplied, every one of these activations has to be multiplied by every one of these weights. So we just go ahead and do that. We build we fetch the weights W at a time, we fetch the activations M at a time. We build a big M times W multiplier array. We multiply every weight by every multiplier, and then we sort out where they want to go. And it turns out if you take the X and Y coordinates of these, you add them together, that gives you the X and Y coordinate of the output activation they need to be summed into. And so we use an operation that I actually wrote a paper about in supercomputing in 2005 called scatter-add, and built a scatter-add unit to basically sort all those output activations out. The energy efficiency here for SCNN winds up being about 3x over doing the dense computation when you have about a 30% density of weight. So it's achieving very good efficiency in exploiting sparsity. Now it turns out this is actually from an accelerator that we haven't talked a lot about yet, so I can't give you the details of this accelerator. But if you start looking at some of the best ways we know of building accelerators, they start to be dominated not by the arithmetic, but by moving data around, by memory access, and a lot of memory access is actually moving data. To give you some numbers, the real figure of merit for doing inference, actually for doing training as well, I think it is femtojoules per map. And that's not just measuring the femtojoules of the arithmetic unit. That's a relatively easy thing to get down. It's the femtojoules of everything divided by the number of macs. And for our NVDLA, which is about the most efficient unit I've seen to date, that number is 200 femtojoules per mac. The number here with full voltage scaling is on this axis, is the femtojoules per mac axis. And you see we're right around 80. It's actually some slightly newer results we have from this accelerator where it's around 70. And I'm actually quite confident we can get it under 50 femtojoules per mac. But part of what we have to do to get down there is to realize at this point we've reduced the arithmetic, which are these two blue areas, to under 20 with aggressive voltage scaling. And the SRAM axes, the weight buffer and the activation buffer, which are these green areas, are starting to dominate everything. And that basically says we have to really worry a lot about how we access memory, make memory access very efficient, and make data movement very efficient. And so, for example, one project I started in NVIDIA research was to look at how to improve the efficiency of data movement by a factor of 4. And it's basically by using every electron twice. This is a paper we published in ISSCC in 2016. We start out by starting with an electron at VDD. We use that electron to drive one signal in this upper tier. Then we get down to the V mid, so instead of running at a 1 volt supply, this is at a half a volt. Then we use that same electron to drive another bit. And it turns out that because energy is CD squared, this is a quarter of the energy of sending the bits. And we basically achieve this with no loss of performance. So we flip the coin around here a little bit, and something that's very important to me as we develop better GPUs, better accelerators for deep learning, is it's important for us to eat our own dog food. So we actually do a lot of deep learning research at NVIDIA Research as well. I'm going to go through this quickly because I see the countdown to lunch going on here. We do a lot on perception. We currently have the state-of-the-art in semantic segmentation, the best optical flow neural network. I encourage you to read this CVPR paper because this is a great example of how, rather than throwing away computer vision research of the last 20 years, we took the best computer vision research for optical flow, and then we applied machine learning to make it better, because it actually combines the best of both worlds to get results that are better than the people who try to do end-to-end deep learning to learn optical flow. We very often have 3D data, so if you have a LiDAR, we can do semantic point cloud segmentation from LiDAR data. Because we are still a graphics company, we spend a lot of time applying deep learning to graphics, both for content creation. A lot of people don't appreciate it, but the gaming industry is bigger than the motion picture industry in terms of dollar revenue per year. Perhaps if they held Oscars, it would get more attention. And a big thing, the big limiter there is artist time. They spend a lot of time basically manipulating what are called rays, with typically 300 control points to basically animate faces. We were able to apply deep learning to take an audio stream and manipulate the faces. We also applied to classic graphics problems like denoising, anti-aliasing, and scheduling where to catch the rays in ray tracing. A really important feature here is in the denoising. To produce a motion quality image with ray tracing, it takes about 10,000 rays per pixel. If you're doing that at 4K, where you now have something like 8 billion pixels, the number of rays you have to cast is enormous. It winds up taking an hour to cast an image. The image to the left is 5 rays per pixel. You see, it's very grainy. It's like you would get if you set your camera at a very high ISO. The image to the right is that same image after passing it through a neural network that denoises it. And this technology has enabled us to, with our RT cores in Turing, ship a product that for professional graphics could do ray tracing that is absolutely as good as the best motion pictures at about 5 frames per second. It's not good enough for real-time graphics yet, which requires 60. We actually, for real-time graphics, use the ray tracing for shadows and reflections, but we can do complete physically based rendering with path tracing for professional graphics at things that architects and automotive designers find very acceptable frame rates. Now I have to say that Terry really set me up for this. The progressive GAN work he talked about is a product of NVIDIA Research, our group in Helsinki, Finland. And the problem they addressed was that training GAN, a generative adversarial network, where I basically feed a random variable into a generator, it produces an image, and I have a discriminator network that basically just says real or fake. You have to realize that the generator network has never seen an image. It simply tries things and tries to fool the discriminator. You're training them both at the same time. But the problem we found, being in graphics and wanting to do high-resolution images, is it was very hard to generate a high-resolution image because you had too many unbound variables you were trying to learn all at the same time. And it would basically get stuck, it would not converge, and things would be really awful. You'd produce awful images. GANs are a wonderful technology invented by Ian Goodfellow when he was at Toronto, a student of Jeff Hinton's. But they required a lot of careful care and feeding. What we realized that this was basically trying to teach the network differential geometry before mastered basic arithmetic. And just like a student that you're trying to teach math to, what you do is you start simple. What you would do is you would start saying, okay, let's start with adding. We'll teach you how to add numbers. Then we'll move on to multiplication. Later on, maybe basic calculus. So the first place we start is with 4x4 images. We feed the random number in, we produce a 4x4 image, and this basically trains both the generator and the discriminator on an easy problem. When they get the easy problem right, we go up to 8x8. When they get that right, we go up to higher resolution and so forth. And here's the movie of training this. This shows the resolution that we're currently training at, the amount of training time. And by mastering each level of resolution before moving to the next, we were able to be the first to generate high-resolution images that actually look really good. Let me move on. It also says that you can now take that random number that's feeding into the network and sweep it around, and you can sort of continuously vary from one image to the next. There are people now who are able to separate those latent factors into different terms. You can have hair color be one, gender be one, facial hair be one, and sweep those variables independently and get these. So let me wrap up and try to keep us on time into lunch. It's a really exciting time to be building computers because the whole application area is changing. Deep learning is doing a revolution in AI that's affecting every aspect of our lives. And this revolution has been enabled by hardware. All of the algorithms have been around since the 1980s. It wasn't until we had, in 2012, we had GPUs with enough horsepower to run them on a reasonable data set in a reasonable amount of time that we really ignited the spark that set off the deep learning revolution. And today, that deep learning revolution is being paced by hardware. As we go to more complex models with larger data sets, that quadratically increases the amount of computation that we need to use to train those models, and we need more powerful computers to train them. In an environment where Moore's law is dead, we're not getting any more performance out of semiconductor technology. And so our solution for this is accelerated. And GPUs provide the underlying platform, the base memory system, the programmable core operations into which we can plug in special purpose accelerators, our tensor cores, our ray tracing cores, double precision floating point for scientific computing. And these are currently the most efficient both